All right. Hello, Science 10 people. Here we are at Kinetic Energy worksheet that I sent out yesterday. And so we're going to go over the solutions today and see if you have, see if it helps answers any of the questions you might have had. So let me just recap quickly though. We've been talking about potential energy, gravitational potential energy, and energy that is stored that can be available to do work at another time. And so the symbol is EP, and now it's been equal to mgh, where m is the mass, g is the gravitational field strength of 9.8, and h is the height in meters, and the units of joules, or sorry, of energy being joules. So when we drop something, though, it begins moving, and that motion can then do work as well. And you can think of, dropping a book onto an egg. That egg is going to get smashed because the book that was falling and moving is then doing work on that egg. And so we talk about the energy of motion, the kinetic energy, and that's equal to 1/2 mv squared, where mass is again in kilograms, v is the velocity in meters per second. Don't forget you need to square the value, and that gives us our kinetic energy in joules. So I like this worksheet because it, first of all, is really getting you to think about the relationship between kinetic and potential and to recognize what's kinetic and what's potential. So a bicyclist pedaling up a hill. Well, he's pedaling up a hill. That really is motion, and so there's kinetic energy. The funny thing about it, though, is that what we have is he's putting kinetic energy into it. There's mechanical energy. He's turning the pedals and the cranks and so on, but he's going up a hill, so he's also gaining some potential energy. So just something to be aware of. Get it out of there. A volleyball player spiking a ball. A spike is a hard hit, so the ball moves quickly. That would be kinetic energy. Go away. All right. An archer with his bow drawn. I did question 1, then question 3. I'm sure some of you did the same thing, but you're still mocking me, I know it. So number 2, an archer with his bow drawn. So he's pulled the string back, the arrow is there. That is potential energy. It's not moving yet. When he releases it, then it's going to be kinetic. A baseball thrown to second base. I used to play softball, and for a few seasons I was the catcher, and that was always the big throw. Somebody's stealing, going from first to second, and so you had to get the ball, get up, and throw it quickly to second base. So the ball is thrown, it's moving. There's kinetic energy. Chemical bonds in sugar. Well, the sugar is just sitting there on the table. That's potential energy. We can use that sugar, we can eat it, it goes into our bodies, our cells do respiration, producing the ATP and so on, that our body that can then change into motion, but that is potential energy. The wind blowing through your hair. Yeah, I've got hair flowing, but it's blowing, it's moving, that's kinetic. So really the question, if it's moving, we're going to have kinetic energy. If it's not moving, if there is no motion, chances are we're talking about potential energy. Walking down the street, looking cool, didn't say that, but yeah, looking cool. We're walking, we're moving, that's kinetic energy. Sitting in the top of a tree, well, that's just potential energy. You have the potential to break branches as you fall and to break your arm or leg or neck as you fall further down as well, but that's just potential. You haven't done it yet. A bowling ball rolling down the alley. Well, that's kinetic. It's moving down the alley. A bowling ball sitting on the rack. Sitting. It's not doing anything. That's going to be potential. Interesting how the first one, perhaps some confusion. Let's continue going on. What's an example you can find in your, what examples can you find in your home that are examples of kinetic and potential energy? Name 2 for each type of energy. Kinetic. Things that are moving, like a blender. You put everything in there, you push the button, things are moving, kinetic energy. Something else that's moving, like a fan. A fan is spinning and blowing air, so that could be kinetic energy. Just two examples. You don't have to give these examples, but if you did give these two examples, you get a bonus 10 marks. Yeah, 10 times the marks on those ones. Potential energy. A glass in the cupboard. If that glass falls, it cracks on your counter. It has potential energy. The book on the top shelf of the bookcase, it has potential energy. Those things can fall, hit you on the head, and hurt you. Again, if you have those two things times 10 marks, you get 10 times the marks. All right, the blank an object moves, the blank it has. So we could talk about the faster an object moves, the more kinetic energy it has. The greater the blank of a moving object, the blank it has. The greater the mass of a moving object, the more kinetic energy it has. Kinetic energy depends both on good looks and a sense of humor. No, mass and velocity. I depend on good looks and a sense of humor. Mr. Eichel's just sitting over beside me. He's doing his work in my room, and yeah, he's laughing. All right. So solve the following word problems using the kinetic and potential energy formulas. Be sure to show your work. Here's our KE 0.5 mv squared, or what we've been doing is EK is equal to 1/2 mv squared. And over here we have EP is equal to mgh. Now, you're going to see this different times, different references. Sometimes we'll talk about KE for kinetic energy. I did that for years. In physics 11 and physics 12, they really began in recent years going E sub K and E sub P. And so that's sort of the notation that I began adopting. E, because it's always the energy, and then the sub to differentiate between kinetic and potential. Velocity, mass. Okay, so here they're using G as 10 meters per second, which is the same thing as 10 meters per second squared. But we've always been using 9.8. All right, you serve the volleyball with a mass at 2.1 kilograms. The ball leaves your hand with a speed of 30 meters per second. The ball has, well, it has kinetic energy because it's moving. Calculate it. All right, so again, what do? We take a look at the numbers. Here we have 2.1, and the unit's kilograms. What does that represent? Well, that's a mass. Then we see through here, we have 30 meters per second. What does that represent? That's a velocity. All right, we're calculating kinetic energy. The formula for that, EK is equal to 1/2 mv squared. Let's substitute in our values. What's the substitute for 1/2? It's a constant. We leave it as 1/2. Our mass, 2.1 kilograms. And then our velocity is 30. But don't forget, you have to square it. So we go 30 squared, and that's equal to, yeah, I'll do this in a couple steps here. So that's equal to 1/2 times 2.1, and 30 squared is 900. We have to do that first. Don't forget, you have to remember bed mass. And I know there's a different one other than bed mass, but all I remember is bed mass. All right, so if we do this, we got 900. So now we just have to go 1/2 times 2.1 times 900. And we get a value of 945. Erase that and try that again. 945 what? Well, that's our joules, because we're talking about kinetic energy. All right, so there we have our first one. Here's our second question. Baby carriage is sitting at the top of a hill that's 21 meters high. The carriage has with the baby has a mass of 1.5 kilograms. The carriage has blank energy calculated. Is sitting. Is it moving? No, not moving. It's at the top of a hill. So this has potential energy. All right, so let's go through and figure out, because now we have to calculate it. We need to figure out what numbers we have. 21 meters. 21 meters. What does that represent? Oh, that's our height. That's how high we are. The carriage with the baby has a mass of 1.5 kilograms. Pretty light baby. 1.5 kilograms. Okay, and that's going to be our mass. Potential energy. All right. EP is equal to mgh. I want to see these numbers. I want to see the formula. I want you then to substitute in. Our mass is 1.5 kilograms. Our G is our 9.8 newtons per kilogram. Oh yeah, that's the other thing. This is the same thing as newtons per kilogram. Well, I've been using newtons per kilogram. It's also equal to meters per second squared. Science is like that. All right, and then we have our height, and that's our 21. So now you pull out your Casio FX260 Solar, 1.5 times 9.8 times 21. And so that's equal to 308.7, and we could say 310 joules of potential energy. Excellent. Let's go on. A car is traveling with a velocity of 40 meters per second, has a mass of 1,120 kilograms. The car has what type of energy? Well, it's a car. It must be going up. No, there's no hill. It's moving. So this is going to be kinetic energy. You got to be able to read the question. Word problems, used to hate them. Probably still do. But word problems, you have to be able to read them, pull the information out of it. All right, let's take a look at our numbers. Here we have 40 meters per second. What is 40 meters per second? Well, that's a velocity. We have the word velocity telling us that. And then we have 1,120 kilograms. What do we measure in kilograms? Mass is measured in kilograms. Any other numbers in there? Nope. And we are looking to calculate the kinetic energy. So what's our formula for kinetic energy? EK is equal to 1/2 mv squared. You've got your cheat sheet, you have your reference sheet beside you. You should always have that beside you when you're doing work with questions like this. All right, so here we have our formula. So now we're going to plug in our values. What's the value for 1/2? 1/2, trick question. What's our mass? Our mass is 1,120 kilograms, and our velocity is 40. Excellent. So now we're ready to go on and calculate this. Wait, sir, wait, you forgot something. What did I forget? What did I forget? Oh, the squared term. You don't want to forget to square that. All right, so let's go do this. So we're going to go 40, and we're going to square that. And so we're going to have 1/2, because we have to do the square first, 1120, and our squared, 440 squared is 1,600, just like that. So now we can go times 1120 times 1/2, and here we get a value 896,000 joules. That's our kinetic energy. We could take 3 zeros off of this, and we could say that's 896 kilojoules. Because joules and kilojoules are thousands of joules, and so it just makes our numbers easier to see and work with. All right, either of these are perfectly correct. A cinder block is sitting. What's a cinder block? Well, that's one of those concrete blocks that they use for building walls. You've got 2 holes in either end of it, and they sort of look like this. They might have a bit of motion at the end, and they stack them up with concrete in between. A cinder block is sitting on a platform 20 meters high. It weighs 7.9 kilograms. The block has sitting. It's not moving, so it has potential energy. All right, so let's go through and find our numbers. We have 20 meters. 20 meters. What does that represent? Well, that's our height. 7.9. 7.9 what? That's 7.9 kilograms. What do we measure in kilograms? Mass. We're calculating potential energy. What's the formula for potential energy? mgh. All right, now we can substitute in our values. Our mass, 7.9. Our value for G, It doesn't mention G. Oh, right, G, 9.8 newtons per kilogram. And then our height of 20 meters. What's that? Look like 28. Anything squared? Nope. Excellent. So now we can just go, just multiply these together. I'm going 20 times 9.8 times 7.9. It doesn't matter the order you multiply things together. So 4 times 3 is equal to 12, and 3 times 4 is equal to 12. I believe that's the commutative property of multiplication.
When they switch order, yeah.
It's one of those technical terms you're taught at some point and then you sort of forget. Anyways, we come up with a value of 1548.4, and well, let's call this 1500, and that would be joules, and that's potential energy. Excellent. You don't have to round this down like this. You don't have to. I'm just doing it so we can see. All right, question number 19. We're scooting through these ones, ladies and gentlemen. A roller coaster is at the top of a 72-meter hill. You know what? I haven't drawn any pictures. Well, I drew that cinder block up there, but this is a roller coaster. So here's my roller coaster. There's the wheels, cart. Here's the cart. Here's the cart. And here am I sitting at the front. I got my arms stuck up in the air. Yee! All right, a roller coaster is at a 72-meter hill and weighs 134 kilograms. The coaster at that moment has what sort of energy? Well, look at this. It's a roller coaster. It must be not moving at all. So it has potential energy. All right, so we've got our numbers in here, 72 meters. What do we measure in meters? Height, distances. So there's our height. 134 kilograms, 134 kilograms. All right, what do we measure in kilograms? Mass. Potential energy, EP is equal to mgh. So now we can substitute in our values. What's our m? 134. What's our g? Oh, right, 9.8. Mr. Johnson, stop freaking out. All right, and then we have 72. And so now we just multiply these together. 134 times 9.8 times 72. And we get a value of 9455.0.4. That's a pretty big number. We'll just leave it there. It's joules. Cool. Here we go, 20. There is a bell at the top of a tower that's 45 meters high. The bell weighs 19 kilograms. The bell has potential energy. Calculate it. Well, let's find out our values. We have 45. 45 what? Meters. What do we measure in meters? Height. 19. 19 what? 19 kilograms. See, it's really important to have the units there, because if you don't have the units, then it's just a number. You don't know what it refers to, and that's going to be our mass. So our potential energy is equal to mgh. Notice every time I'm writing down the formula. Every time I want to see you writing down the formula as well. So we substitute in our mass, 19 kilograms. Our g, well, no, that's 9.8. We're getting better at that. And now our height, which is 45 meters. And so we can take these and go 19 times 9.8 times 45. And we get equals to 8379 joules of potential energy. Determine the kinetic energy. Oh, they're telling us what to do now. Oh, I hate being told what to do. I guess we'll do it. Determine the kinetic energy of a 1,000-kilogram roller coaster that is moving with a speed of 20 meters per second. All right, so we know we have to find kinetic energy. That's what we're trying to find. So let's write down EK question mark. Then we have our values. Well, we've got 1,000 kilograms. Well, what are we measuring in kilograms? Well, I'm measuring mass. Then we have this 20 meters per second. 20 meters per second, speed, that's our velocity. Excellent. So how do we calculate kinetic energy? EK. Is that mgh? Is that 3/4? Okay, I'll look at my sheet. Oh, right. Kinetic energy, 1/2 mv squared. Write down the formula. Notice that's a different formula. I know you're using the right formula when you write down the formula that you're using. You got a choice of 2. That's why. All right, Now let's substitute in our values. So we have 1/2. We have times our mass. That's equal to 1,000 kilograms. Then we have our velocity. That's equal to 20. Now we're ready to... Hold on. Don't forget. We have to square it. Yeah. Don't forget. Square, square, square. So we have to do the square first. That's equal to... So we have 1/2 times 1,000 times 20 squared. 2 times 2 is 4, and then zeros. That's equal to 400. So now we can just multiply these together. And we get 200,000 joules. Just that easy, ladies and gentlemen. Just that easy. All right, 22. The roller coaster in this car above was, if the roller coaster in the above problem was moving at twice the speed, then what would its new kinetic energy? Remember, we had to talk about this before. And this comes down to it because when we calculate kinetic energy, it's equal to 1/2 mv squared. So when it's v squared, if we're doubling the velocity, the 2 in front of the velocity gets squared, so it'd be 4, and the kinetic energy be 4 times the amount. So our kinetic energy would be our 200,000 times 4. So that would be 800,000 joules of energy. So you could think about it and work with it that way. Or you can come over here and we can just do our EK is equal to 1/2 times 1,000. Now instead of 20 meters per second, it's going to be 40 meters per second. And we have to square that. And lo and behold, we get this answer that says it's 800,000 joules. Same thing. Here we thought about it and recognized that when the velocity doubles, the amount of kinetic energy is quadrupled. If it was tripled, then the kinetic energy would be 9 times greater. So you have this, the squared of the velocity that affects the kinetic energy that's there. But you can also plug it in and it works out fine. Question number 23. A cart is loaded with a brick. Must be a small cart. You know, one of those lab carts that we've got in here, and we put a brick on top of the cart, and we're pulling it along. So a cart is loaded with a brick and pulled at a constant speed along an inclined plane to a height of a seat top. Oh, gee, I blew that one. So we have to take this thing, and then we have to rotate it. There we go. Let's go back. All right, to the seat top, if the mass of the cart is 3 kilograms, and the seat top is 0.45 meters, then what potential energy does it have? All right, so let's, potential energy. Potential energy is equal to mgh. It's being pulled at a constant speed. Yes. So it has kinetic energy, but we're concerned about the potential energy when it gets to the top. Right, so we know the 3 kilograms, so that's our mass. And we have this 0.45 meters. What does that represent? That's our height. All right, so we substitute in our values. 3.0 times our GG, oh yeah, 9.8. And then times our height of 0.45. Then no squares, so we just go through and multiply these. 3 times 9.8 times 0.45. And we get a value of 13.23 joules, or we could just say 13 joules. That would be good enough. Oh, we're getting close to the end. We got the refrigerator on the 70th floor of a high skyscraper. All right, a 75 kilogram refrigerator is located on the 70th floor of a skyscraper 300 meters above the ground. What is the potential energy? All right, potential energy is equal to mgh. All right, so let's take a look at our numbers. We've got 75 kilograms. We're going to take our 75 kilograms. That's our mass. We have the 70th floor. What do we measure in 70th floor? Nothing. So it's a number, yeah, but it's not going to be part of our calculation because we're told we have this 300 meters, and that is our height. So there is a relationship between these. In fact, we could calculate, take this, divide it by 70 to find out how tall each floor is approximately. Um, but yeah, this 70 isn't necessarily used. So yeah, recognize that not always will every number from a question be used. You have to still think. All right, so let's calculate our potential energy. Our mass, 75 kilograms. Our G, 9.8. And our height is 300 meters. So we just multiply these together. 75 times 9.8 times 300. And we get a value of 2,20500. I'm just going to do that one more time. Calculating things twice is always a good way just to make sure you've done your calculations correctly. Also, taking a look at a value and does it make sense? Calculators lie. Even the Casio FX260 Solar. Sometimes I punch things in correctly, push the equal sign, and it just lies to me. So you need to be able to take a look at your number and make sure it sort of makes sense. This number was so large, I didn't really know if it made sense or not. And so just going through and punching it in again, coming up with the same value, it sort of reassures you that you've done the calculation correctly. All right, question number 25. Potential energy of a 40 kilogram cannonball is 14,000 joules. How high was the cannonball to have this much potential energy? We're talking about potential energy. EP is equal to mgh. Let's take a look at our numbers. All right, we have 40 kilograms. What do we measure in kilograms? Mass. Then we got this 14,000 joules. What do we measure in joules? Energy. In fact, it's potential energy. What are they asking for? The height. But hold on, height is way over there. How do we do this? That's where I've given you the different formulas. We can do the algebra, and height is just going to be equal to our potential energy divided by our mg. Okay, so you can have this written out on a cheat sheet. That's not a problem. So let's substitute in our values. Height is equal to our potential energy is 1,000 so many joules. Our mass is 40 kilograms. And then our G, right? You have to remember that, 9.8. So now we can just plug in our joules. Or plug in our calculator. 14,000 divided by 40 divided by 9.8 equals 35.7 meters. That would be our height. Okay, and let's come down to our last question. If most of the energy we use on Earth comes from the sun, and that's true, how does that energy, light and thermal, end up as energy in our food? Well, photosynthesis. Yep, bringing stuff in like that. As energy of wind or moving water. Well, okay, so photosynthesis, this is chemical energy. The wind moving water, we can think of that as mechanical energy. May have been too specific on this answer up here, photosynthesis. As the energy that powers our light, so we can talk about electrical energy. And energy that when we move around, that would be good mechanical energy again. So let's talk about this electrical energy. Where does our electrical energy come from? Our electrical energy comes from let's change colors just because I can. We have water, and the water comes through, and it spins a penstock, which turns a generator, which produces electricity that we then go out. Well, how did the water get up here? Well, the water was running down a mountain stream. Well, how did the water get to the top of the mountain stream? And that's because at the ocean, you've got water, and then you have the sun, and the sun sends down its heat, and that causes the water to evaporate, which forms clouds, which blow over to the mountains, and then to end up raining on the mountains. So it's the sun that is providing the energy that moves the water so that we can use gravity to produce electricity to turn our lights on. The blue light. So recognize the sun is pretty important in terms of energies and so on. All right. If you have questions, don't forget you can always contact me. So today is your second day for doing this. I'm thinking that I might give you one more worksheet tomorrow and have a couple days to work on this as well. Just dealing with kinetic and potential energy just as further review for you. All right. Have a great day. Have a day. Talk to you again.